And I'm going to talk today about strong correlation that elucidate the electronic structure and phase diagram in STO-LAO interface. Okay, so we'll start with the motivation. Our motivation starts with, as you saw in the morning, superconductivity. And this is a measurement of superconductivity in STO-doped, delta-doped. That is the niobium dope from the Paris group. As you can see, and as you heard in the morning, the superconducting dome is a wide range in carrier density at the bulk of STO. And this red part is an approximation of carrier density for STO-LAO from this group. Now, again, as you saw in the morning, Caviglia was the first one who measured this superconducting dome at the STO-LAO interface, but the main difference, or one of the main differences between this graph and this graph, is the x-axis, which is gate voltage and not carrier density. We'll go to that in future slides, but keep that in mind. It is not directly the gate voltage, which is implying the carrier density. Another thing is the reasons for this ruining of superconductivity, as was talked this morning. So for the underdoped side, we heard a lot of reasons. Some of them are the 2D fluctuations, okay, 2D superconductivity fluctuations. But on the overdoped side, there is no real explanation or good explanation till now. And we are going to try, one of our motivations is to try to explain why the superconductivity decreased on this overdoped side. Next slide, or next motivation, is the transport properties of this material. Also a bit complicated because of the band structure. So there's two methods we can measure carrier density with transport measurements. One of them is the Shubnikov-Das oscillations, which actually probe directly the mobile band. If we have some bands, okay, more than one, if there are enough mobile, okay, we will see different frequencies. And STO-LAO, as you can see here, this paper in 2010 from our group, only one frequency is observed, okay? So from this frequency you can get the carrier density and know exactly the carrier density of the band. Simultaneously, the Hall was measured, the Hall resistance, and as you can see here, the Hall resistance is not linear. This is something that implies that there is more than one band involved in the system. So this equation is this long equation, yeah, is an equation for a two-band model, which involves two bands that have different carrier densities and different mobilities. And what they did here is just imply the fit of this model and got two different bands that has two different carriers. Okay, the red band here, the red graph is the low carrier one, which has higher mobilities and should be reconciled with the Shubnikov carriers, and the blue one is the higher carriers, and has the lower mobility. But from experiment, okay, from the Shubnikov experiment, this carrier density does not reconcile in almost an order of magnitude. So this is another problem we're going to try to solve. Why doesn't the Shubnikov-Das measurement doesn't fit this two-band Hall data? Okay. So let's start. Our experiment starts with measuring of superconductivity. And as you can see here, this beautiful graph actually reproduced the Caviglia dome in only 15 volts because of our enhanced device. In blue is the superconducting state, and in red is the normalized state. It is all in the normal state. The resistance is normalized here. And it is the temperature versus the gate voltage. And in the right graph, you can see magnetic resistance measurements from which we can calculate the critical field. And simultaneously, we measured the Hall resistance, and from which we can calculate the inverse Hall coefficient, which actually is the carrier density inferred from the Hall. And if we do that, we get something interesting. Okay, the blue diamonds are the measurements of the critical field, which goes like more like the TC dome. But in purple and yellow squares, you can see the inverse Hall coefficient, okay, in low field regime, which is much more simple to understand. And it also actually behaves in a non-monotonic behavior, okay, going up and down. But because this is a Hall measurement, which is actually pretty complicated and involves the two bands, we don't really know what is happening between the bands themselves. We can actually predict a lot of stuff. So we needed much more accurate or much more direct measurements of the bands. So we went to high fields and measured them their some samples to measure the quantum oscillations. Here you can see on the left the Hall plots, and on the right you can see the longitudinal resistance after subtraction of a polynomial fit, and after applying for each of these oscillations a fast Fourier transformation, we can get for each gate voltage the frequency. And after we do that, we get something really surprising. So, and the surprising stuff here is the green graph, okay? The blue graph is just the Hall inverse Hall coefficient, which is the carrier density inferred from the Hall, and it's actually behaving the same way it behaves when we measured it simultaneously with the superconductivity. But what is really interesting here is that the green plot actually goes up and down with the gate voltage. What does it mean? That actually the band, the mobile band that we are probing, is increasing with carrier density, and at a certain point it's decreasing, okay? And this is a direct measurement, it's not some kind of estimation. This is the quantum oscillation frequency on the right. So our main question now is what causes this behavior, and why do when you increase the gate voltage, carrier density does not increase also, okay? And what is the reason for this non-monotonic behavior? So let's try to look at the two-band model, okay, that will imply on our measurement. So if we look at a two-band simple, higher blue band and lower red band, and chemical potential in the black, when we increase the chemical potential, we just populate the lower band until we reach a point that we are populating and reaching the second band. And at a certain voltage, as we saw from the Shubnikov dust measurement, okay, we reach a maximum, and from that maximum, somehow the bands shift, okay, and the electrons go and move from the unpreferable blue band to the preferable energy lower red band. So how can it be, and what kind of physical interaction can explain this? So we talked a lot and collaborated with Moshe Goldstein, and we got to this explanation that electronic interaction can cause a competition between the occupancies of different bands, okay? Electron-electron repulsions. And in such the presence of such a competition, occupying the band with the highest single particle density of states is usually preferable, since this results in a lower single particle energy. Okay, so this should explain why our band structure is not rigid. Okay, and when we change actually the chemical potential, we change the structure of the band structure. Okay, and one more thing, Q does equal CV, but it's for the total carrier density, okay, of the system. And an interplay between the bands themselves changes what we see if we probe only one band. So after realizing this, we just needed to calculate it. It's very simple, or not. As you know, band structure of LSTO, LAO is very complicated. So we started with the T2G titanium D orbitals, as mentioned in the morning. In the bulk, they're degenerated, and on the surface of STO, as shown by Sandro Nasiro in Ampere's measurement, the confinement of electrons does lift the degeneracy between the XY band to the other XZ and YZ bands. Other or previous measurements or calculations that were done on those band structure involved atomic spin orbit, okay, which created a mixing of those three bands into three new bands, okay, as you can see here by Joshua and Wuchman. And we used all of this basic knowledge to write our Hamiltonian. So we have our tight binding of the 3 titanium d orbitals with our 2 transfer integrals and our Herpin term. We add this atomic spin orbit interaction, okay, added by Wuchman and Joshua. And we ourselves are adding an mean field intra and interband electron-electron repulsion, okay, in the diagonal part of this matrix. Now all there is to do is to solve this Hamiltonian, okay, self-consistently for each chemical potential, and just plot the band structure, the different band structure for each chemical potential. So this is an example for 3 different chemical potentials. As you can see here, if you look closely, the band structure is changing, okay, between low chemical potential and high chemical potential. And after you get this band structure for each chemical potential, you can just sum up the places for electrons to be in the band structure and get the carrier density. So we did that also, and we got that the lower blue band, red band is just monotonically increasing with carrier density, but the lower mobile band is a non-monotonic, as a non-monotonic behavior with changing chemical potential. With that, we also calculated the density of states of that blue band, okay, the mobile band, and we see, of course, a non-monotonic behavior of the density of states. And remember this for a future slide. And also we, with the 2 carrier density that we calculated, we could calculate in yellow the Hall or the inverse Hall coefficient with this low field Hall approximation that you see here. So comparing the experiment to the model we gave, you can see here in the blue is the carrier density inferred from our calculation, okay, and in the green is the carrier density which is inferred from our Shubnikov-de-Haas measurement. So it's in the same order of magnitude and the same behavior, and also Vg and the chemical potential are scaled through the capacitance of the STO. So this is actually reconciling the transport property that didn't agree before for the low carrier Shubnikov-de-Haas measurement. Moving to superconductivity, so we used a simple, okay, because we know our density of states is non-monotonic, we just decided to use the simple model of weak coupling BCS, okay, as was mentioned again in the morning. V is the density of states, and N is the electron-phonon coupling. We took the Debye temperature from specific heat measurement of STO, plugged it in, and calculated the critical temperature for our system. And as you can see here, you can see a non-monotonic behavior. In blue, it's our calculation that resemble our measurement in the purple. And actually what it can mean, okay, that the second band, at least in the overdoped side, is responsible for the decrease in superconductivity. For the underdoped side is a different regime and can be explained by other explanations. So, summarizing, measurement of Shubnikov-de-Haas, Hall, and superconductivity show the same non-monotonic behavior. We suggest this model of electronic correlation to explain this behavior. Using this model, we reconcile all the transport properties, and using this simple BCS model, or theory, we obtain a non-monotonic TC versus gate voltage behavior. Thank you.
at least the way of thinking is very similar to Stoner instability. That basically, instead of the two bands, I will call one band spin up, one band spin down. But it doesn't look like you have any transition in your curve. I would expect some kind of cusp in the density as a function of gate voltage.
What do you mean transition?
Basically, at the point where it becomes energetically favorable to start to occupy the first band.
The first or the second? The superconducting band?
No. Okay. You had the two bands, one was at lower energy.
Yeah.
So basically, at a certain point, you are populating it further instead of the higher energy band. Right? You are starting to deplete electrons from the higher energy band.
Yeah.
Now, I would assume that there will be some transition point where it starts to happen.
Yeah, there is a point where the lower band, okay, is actually there's not only a shifting of bands, but the bands themselves change the structure. I can't answer you like immediate answer now, but I can look at it. But the shape of the lower band itself does change, okay, with the chemical potential. So I can look at it.
Maybe I should add that all those bands there are all kinds of mixing terms. So you cannot get something sharp because it's not like a magnetic resolution. It's more like a magnetic stone instability in the presence of a magnetic field with components in all directions.
You're talking also about the two bands
of superconductivity? It's not going to be sharp.
We're talking about at least one band. Okay?
One band superconductivity.
Yeah.
Only one band is so.
This is our implement for the decrease.
I'm not sure how you gauge your sample, but what we see is that in the overdope regime, the confining potential is changing, which would also change the electronics structure. Now I realize that an opening would not go in the direction you need to explain that you're emptying the heavy band. But did you consider the fact that the confining potential would change?
Yeah, it can be an explanation. Actually, our devices are gated a bit differently. They're gated as a backgate, of course, but we have a unique geometry that allows us to gate it much more efficiently than the ordinary gate. Like you can gate it, as you saw, like an order of magnitude higher. So.
But could that account for the Shubnik of the hasp behaving non-monotonically?
I guess not what I showed, but if you would close, or if you would confine a little more, probably you would push the heavy band higher, which is not what we see. So I'm not saying it's this.
But regarding the non-monotonicity, could you consider also a scenario that is similar to Emery and Kibelson for high TC? Because as you shown, the data from Henard, so the gap, the measured superconducting gap increases as you go to the lower doping, which means maybe the coupling strength increases, but phase stiffness, of course, reduces. So maybe this competition between pairing and phase stiffness may also can give rise to this dome shape.
Yeah, we didn't consider that.
But this will only apply for low carrier concentration, and this is focused on the high carrier concentration. So
no, but there is
it's not clear, but that's the easiest way to calculate transition temperature.
So the dome cannot be used as an evidence that this is not BCS. The mere fact that you have a dome could be accounted by BCS. You need to do something else to show that it is not.
Okay, one last question.
So is there any structural change also? The atoms must move as well. I mean, if there's like strong electron interactions in an oxide, but typically there could also be a lattice change, which could account for what's going on as a change gate voltage.
Yeah, we don't know if there's structural change. We didn't.
The X-rays or something to see.
Not on those samples.
Those kinds of temperatures.
Okay, last question.
I thought that the population of the higher band was also associated with emergence of features like AMR and other magnetism in
Okay.
this material. So actually, do you see that suppression of this phenomena as you are increasing the gate?
We didn't measure.
Is it consistent also with magnetic transport measurement that would give you this correlation? I mean,
I don't know.
see the depopulation also manifested in disappearance of AMR as you increase the gate voltage or something like
On our samples,
that? Yeah.
we didn't see it. We didn't look at it.
Okay, so let's thank all the speakers of this session.